Okay, welcome back, everybody. Welcome back. Now it is time to get into the nitty-gritty of key identity stuff. Okay. So what is key identity stuff? Well, um, the uh, the build-up that I did last time was getting ready for some of the complex algebra that was required in doing these things. So I showed you how to compute, you got a complex number, z equals x plus iy. I showed you what the conjugate was. I showed you how to compute 1 over z, right? That's z bar over modulus of z squared, where the modulus of z is square root of x squared plus y squared, and so on. So I showed you all these things. I defined the real part of an imaginary number, so that's x. For this one, the imaginary part, whoops, sorry, of complex numbers y. Both of these are real numbers, right? This was kind of the quick rundown of how this thing goes. Oh, I also mentioned to you, polar form, okay, and how Euler's formula tells you that e to the I theta is cosine theta plus I sine theta. So this gives you this business that e to the I pi plus 1 is equal to 0. Euler's formula, right, emerges immediately out of this, right? So you can see e to the I pi is equal to minus 1, or e to the I pi plus 1 is equal to 0. Very famous formula arises immediately from this. What this is really saying is that e to the I theta, if I track, right, so remember, if I have a point in the xy plane here, I could think of it as complex number x plus iy, or I can say here's my correspondence with just a normal old ordered pair xy here. Okay. All right. And so, what does this, maybe I should say, like, what does this have to do with all the key identity stuff that I want to do? Well, you'll see that in actually finishing these problems, I'm going to need to do a bunch of complex algebra to actually make this stuff work out. Even though the resulting solutions are going to be nothing but real valued, they still have to pass through this. Well, anyway, if that's the case, then if this same point can be thought of as r e to the I theta, and e to the I theta is cosine theta plus I sine theta, then really that's me passing to r cosine theta, r sine theta. So this is just polar coordinates, as I mentioned yesterday. Okay, so this is really just polar coordinates here, r cosine theta, r sine theta. That is viewing this point as being on some circle of some radius centered at the origin. Right, so, oh, there's my radius. Hey, wouldn't you know that r is actually square root of x squared plus y squared? Hey, that's the modulus of z, just like I said yesterday. Right? And that theta is this angle measured counterclockwise at the positive x-axis. So e to the I theta is something that's tracking unit circle. Right? This tracks unit circle. Unit circle in the plane. All right, so I know that that's a lot of info on, hopefully, refresher. Maybe you remember seeing this before. If not, then this is kind of the basics of what you need to know in order to do some of this simple complex arithmetic. So we're going to do enough examples that you'll see exactly how this is applied for these. So this is the setup. All right. So then what is the key identity itself, right? So The key identity is the following. If I have some non-homogeneous linear constant coefficient equation, so L is linear constant coefficient. This is non-homogeneous because f of t is just some function, but we'll say that it's in characteristic form. Okay. Then what happens if I apply L to e to the zt? Now you can think of this formally as z just being a formal thing here. Typically, we are thinking of z as being some complex number. I'm going to write that complex number as mu plus I nu. I wonder what that came from. Right? But let's say it's L of e to the zt. What is this? If I plug in e to the zt here, or don't think of it like that, think of it as just hitting it with L, what do I get? It turns out that I get p of z times e to the zt. This expression is called the key identity. Okay. Now let's just verify that this actually works the way that it does. So let's verify. So let's look at the equation, and we're going to revisit this equation here in just a second. So let's look at the equation. Y double prime plus 2y prime plus 10y is equal to 6e to the 2t. Now you might remember this is exactly an equation we did a few days ago using undetermined coefficients. So in this case, what is L? L is the operator that takes the second derivative, adds to it 2 times the first derivative, and adds to that 10 times the thing I was taking the derivative of in the first place. Okay. Let's see, what is L of e to the zt? Notice p here, the characteristic polynomial, is z squared plus 2z plus 10. L of e to the zt is what? So this is d squared e to the zt plus 2 d of e to the zt plus 10 times e to the zt. Okay. Let's see what this is. What is d of e to the zt? The derivative, this d is with respect to t. Right? This is a differential equation of variable t. So this is the derivative with respect to t. The derivative with respect to t of e to the zt is z e to the zt. Simple. So then d squared e to the zt is just d of e to the zt. So this is d of z e to the zt. Z doesn't depend on t, so I don't need to do a product rule here. So this is z squared e to the zt. So what does this become? This becomes z squared e to the zt plus 2z e to the zt plus 10 e to the zt. Well, what is that? If I factor out an e to the zt, what am I left with? I'm left with z squared plus 2z plus 10 e to the zt. Oh, but what is that? That's the characteristic polynomial. P of z e to the zt. Hey, what do you know? That works, right? So, what's the deal here? What am I saying? What I'm saying is that you hit e to the zt with L, you get characteristic polynomial of L times e to the zt. This is the key identity. And all the other things we call key identities are derived from this one. So here's an example of how this applies. But it turns out that this works regardless of what problem you're looking at. So long as L is linear constant coefficient, this works out exactly like this. Okay. All right. So this is the key identity. There is another very important fact from which all other key identities are derived. So first of all, let me write the top key identity. So the top key identity, sometimes called the 0th order key identity, is this thing. All other key identities are determined from this using the following fact. I'm going to write that fact here. This is the fact that if I apply L to t to the k times e to the zt, the effect of this is that I take a kth derivative with respect to z of L of e to the zt. This is a very important fact, but how does this work? Okay, how does this work? Well, let's let k be equal to 1, for instance. So what about L of t e to the zt? According to this should be equal to the first derivative with respect to z of L e to the zt. But L e to the zt is p of z e to the zt. So this is the derivative with respect to z of p of z e to the zt. I have to use product rule here since both of these things depend on z. So this would be p prime of z e to the zt plus p of z times z e to the zt. Or, sorry, not z to the zt. I'm taking the derivative with respect to z, so this would be t e to the zt. Okay. So this is an example. This would be the first key identity to be derived from this thing, and I would write this in the other order, so I'm going to write p coming first and then the derivatives going next. So that key identity would be L of t e to the zt is what? This is p of z t e to the zt plus p prime of z e to the zt. If I did this again, this would be L of t squared e to the zt. So now I'm taking a second derivative, which would be, I'm just going to go ahead and write it out. This would actually be p of z times t squared e to the zt plus 2 p prime of z t e to the zt plus p double prime of z e to the zt. I'm going to write out another one and then see if you can guess what comes next. So L of t cubed e to the zt is equal to p of z times t cubed e to the zt plus 3 times p prime of z t squared e to the zt plus 3 times p double prime of z t e to the zt plus p triple prime of z e to the zt. Can you tell what comes next? How am I generating these? If I consider this the 0th order thing, and this is the first, and this is the second, and this is the third, What am I doing here? What am I filling out right now? This is Pascal's triangle. What do these coefficients compute? Coefficients in the binomial expansion of, we'll say, x plus y. So this is x plus y to the n. So this is the 0th level. So this is x plus y to the 0. Its coefficient is a single thing, 1, because x plus y to the 0 is 1. This is the first. This is the n equals, so this is the n equals 0 level. This is the n equals 1 level. So you get 1 and 1 here, 1 and 1. This is the n equals 2 level. So you get 1, 2, 1. This is the n equals 3 level. So you get 1, 3, 3, 1. Of course, you obtain these numbers by adding, so the 1's go on the outside. The number here is the sum of the two numbers to the left and right above it. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then the 1 goes to the outside. Here, 1 goes to the outside. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1 goes to the outside. So this is how these things are generated. You can generate the coefficients in binomial expansion for x plus y to the n using Pascal's triangle like this. So for instance, x plus y to the 5, using this same table, is what? It is 1 times x to the 5th plus 5 times x counts down, y counts up. You can do it the other way too. It's fine. This is a symmetric thing. So x to the 5th plus 5, x to the 4th y. Here the y term was to the 0th, right? So 5x to the 4 times y plus 10, x is counting down, y is counting up, x squared, y squared, right? Plus, x cubed, y squared. Yeah, there we go. Plus 10, x squared, y cubed, plus 5, xy to the 4th, plus y to the 5th, right? That is how you expand a binomial using the binomial theorem as easily as possible, right? These coefficients, of course, are the binomial coefficients in choose k. So if you've ever done any probability, any counting in choose k, those are generated with Pascal's triangle, right? That's exactly where those coefficients come from. All right, so using this counting, so x is counting down, y is counting up. The same thing is happening here. The t is counting down, the number of derivatives is counting up, if you like. Okay, so let's write one more of these things using this pattern. L of t to the 4th, e to the zt is what? This is p of z, t to the 4th, e to the zt. Plus, we're using this line, right? So this is plus 4 p prime of z t cubed e to the zt plus 6 p double prime of z t squared e to the zt plus 4 p triple prime of z t e to the zt plus 1 times p quadruple prime, so the 4th derivative of p, times t to the 0 e to the zt. These boxed things, and of course these keep going, so this will keep going as much as you need. These boxed things, these are the key identities. How many of them are there? Well, technically there's infinitely many, but you will only need to use as many as you need. Okay. How does this work? Well, how do you know how many of these you need? What is the process? So, here's the key identities process. Just like undetermined coefficient set process, key identities process similar. Key identities process. 1. So here's the equation in question. Remember, this only works when L is linear. So L linear, constant coefficient, and F must be in characteristic form. Okay, so F must be in characteristic form. So a lot of restrictions, but assuming all those things work, these are exactly the same restrictions as for undetermined coefficients. Okay, so what's key identities process? So first, write out, or I should say solve, homogeneous problem. So solve homogeneous problem, Ly equals 0 for y sub h of t. That's what we did before. This will, in the process of this, you're going to find the characteristic polynomial, right? So you will find p of z plus roots from this. 2. Write out degree, multiplicity, and characteristic for f. Just like with undetermined coefficients. Step 3, here's the main process. Evaluate the key identities at z equals mu plus I nu. Now, the key identities, I just told you, they're this list, but this list is infinite. So clearly I don't want you to be evaluating infinitely many of these key identities at this characteristic. So which ones? The m through m plus d key identities. So recall how the terms in undetermined coefficients, right, the polynomial terms, counted down from degree m plus d to m. All right, the key identities that you use are going to be, well, there's going to be m through m plus d of those. So just like how when you had an m plus d that was a large number, right, especially when the degree is large, you were going to have a lot of algebra involved in solving for your particular solution using undetermined coefficients. The same thing happens here, where you need to use more and more of these key identities as m plus d is large. Now, as I said, typically this m plus d is going to be small, so you're not going to have to use more than like 2 or 3. 3 would be kind of the absolute most you would need to use. All right, and so evaluate the key identities at this, the m through m plus d key identities, and use algebra. We're going to see how that works to find y sub p of t. This is by far the trickiest step in all of this process, and this is actually where we're using key identities, right? Like steps 1 and 2 I could have done with undetermined coefficients, so this is really where things are going different. And number 4, then the general solution to Ly equals f of t is, of course, as always, y of t, which is homogeneous part plus particular solution. Okay. All right, so let's see how this goes. All right. So the best way to see how this goes is to do an example. Now, in fact, I will be doing several examples, and really there's no way around it. This is kind of the only way you can get comfortable with these computations, is to do example after example of these things. Now, as I said, if you would prefer to just do undetermined coefficients and never touch key identities, that's perfectly fine. You're going to have one homework, which I said I would assign it yesterday, but I'll just assign it here in a little bit. When I stop lecturing, I'll post it, and it'll be due in a couple days. It's going to be the only homework where you're actually forced to it's going to be the only homework where you're actually forced to use one or the other. It's just going to be two quick problems. One will be undetermined coefficients. The other will be key identities. Just for some practice, just to have you do it, in preparation for the exam. Maybe you'll find key identity stuff is not nearly as tricky as you thought, right? In fact, we're going to see how in a lot of ways it's significantly nicer for some problems than undetermined coefficients. So y double prime plus 2y prime plus 10y is equal to 6e to the 2t. This was something we did with undetermined coefficients. Let's see that we actually get the same thing when we do it with key identities. Okay, so my characteristic polynomial, of course, is z squared plus 2z plus 10. Must be probably sick of seeing this by now. So this is z plus 1 squared plus 3 squared. So roots are minus 1 plus or minus 3i. Okay. So this is minus 1 plus or minus 3i. Let's go ahead and write out the homogeneous solution. So general homogeneous solution. That is the solution to the associated homogeneous equation, which is y double prime plus 2y prime plus 10y is equal to 0. Is y sub h of t is c1 e to the minus t cosine 3t plus c2 e to the minus t sine 3t, right? So that's our favorite homogeneous solution. There it is. All right. F of t here, of course, is 6e to the 2t. What's its degree? 0. What's its characteristic? 2. I'll write it as 2 plus I 0. And what is its multiplicity? Well, 2 is not a root of this characteristic polynomial, so 0. Okay. So, going back to my key identities process, I want to evaluate the key identities at z equals 2 in this case. And I'm going to be using the 0th through the 0th key identities. So I should only need the key identity itself. Reminding you quickly, here's my box. Typically, to remember the key identities, I would remember them using Pascal's triangle in this business of counting down. Right, but here I'm only going to need this first one, supposedly. Okay, and so what is the key identity? So the key identity is L of e to the zt is equal to p of z e to the zt. Now, evaluating at z equals mu plus I nu, which is 2 here. What do I get? I get the L of e to the 2t is equal to p of 2 e to the 2t. Well, what's p of 2? P is z squared plus 2z plus 10. So p of 2 is 2 squared plus 2 times 2, so 4 plus 10. So P of 2 is 18. All right. So this is equal to 18 e to the 2t. So L, let me just write that again. L of e to the 2t is equal to 18 e to the 2t. Now, what is this algebra that I'm supposed to be doing? The idea is that I want to find a particular solution, y sub p of t, such that when L hits y sub p of t, what I get is this right-hand side, 6e to the 2t. Now, that's not what I get here. I get 18e to the 2t. But how can I make 18e to the 2t be 6e to the 2t? I would have to divide both sides by 1/3. Or, sorry, multiply both sides by 1/3. I can move that 1/3 into L because L is linear. So whether the 1/3 is inside or outside of L doesn't matter here because L is linear. So L of 1/3 e to the 2t is 1/3 times 6 or 18 e to the 2t, which is 6 e to the 2t. But what does this expression say? This expression says that, oh, I found something that when I hit it with L, I get 6e to the 2t. So this means that that thing inside is my particular solution. Done. So you see how in this instance, this is much quicker than undetermined coefficients because I didn't have to compute a single derivative. I didn't have to plug anything anywhere. I didn't have to do any of that. Here it is, right? Boom, done. So general solution, y of t is homogeneous plus particular. I'm not going to go through the process of rewriting that. You know how to do that at this point, right? I think we can stick those two things together and put a plus sign between them. I have faith in us. So that's it. See how quick that is, right? So that was faster than undetermined coefficients in that case. All right, let's do another example. Okay, so let's do another example. So let's do y double prime minus 6y prime plus 9y is equal to 4e to the 3t. You might also recognize this as something we did using undetermined coefficients. So again, what do I do here? So characteristic polynomial is z squared minus 6z plus 9. Does that factor? Yes, of course it does. This is 7 minus 3 squared. Okay. Okay. Now what? Well, this has roots. Z equals 3, and it's a double root, so I'll list it twice. Okay. So then the homogeneous part, that is the homogeneous general solution. The solution to y double prime plus or minus 6y prime plus 9y is equal to 0 is c1e to the 3t plus c2t e to the 3t, right? This is our usual recipe. Okay. All right. So f of t in this case is 4e to the 3t. The degree is again 0. The characteristic mu plus I nu is 3 plus I 0, so it's just 3. So then what's the multiplicity? Well, the characteristic is 3. 3 is a root of the characteristic polynomial, and its multiplicity is 2. So multiplicity of f is 2. Now, according to my process, let's bring it back. Next is to evaluate the key identities at my characteristic. And the key identities in question are m through m plus d. So that's the second key identity, the second order key identity, through the 2 plus 0, or the second order key identity. So I should still only need a single line of the key identities. But this claims that I need the second order one, i.e. this one. So this claims I should use this one. So let's write that out. So L of t squared e to the zt. What is that key identity? Just copying. All I'm doing is copying this. Okay. So that is p of z, t squared e to the zt, plus 2 times p prime of z t e to the zt, plus p double prime of z e to the zt. Now, I want to take this and I want to evaluate it at z equals the characteristic mu plus I nu, which in this case is 3. So let's plug that in. This implies that L of t squared e to the 3t, is equal to p of 3 t squared e to the 3t plus 2 times p prime of 3 t e to the 3t plus p double prime of 3 e to the 3t. Well, what's p of 3? Here's p. What's p of 3? I plug in 3 here, what do I get? 0. What's p prime of 3? Well, if you don't believe that it's also 0, let's compute it real quick. P prime of z is what? This is 2z minus 6. So what's p prime of 3? 6 minus 6, which is 0. What's p double prime of 3? Well, p double prime of z is just 2. So p double prime of z is constant. So p double prime of 3 is 2. So this is equal to 2e to the 3t. But that's not what I need. I need 4e to the 3t. So if I multiply this by 2, I got to multiply what's over here by 2. This means that L of 2 t squared e to the 3t is equal to 4e to the 3t. That's exactly what I need. So the particular solution is 2t squared e to the 3t. Go back and check when we did this same problem using undetermined coefficients that in fact we got exactly this same particular solution. Again, notice how fast this was. Right? This was faster than undetermined coefficients because I did not have to make any guesses and then plug this into the differential equation, go through this algebra, set things equal to 0, solve those equations. Didn't have to do any of that. Boom. I wrote out key identity, evaluated it, most terms went to 0, and that was it, right? Okay, so that was that. And so general solution is, as always, y of t is homogeneous part that I found up here plus this particular solution that I just found. Okay. All right. More. Okay, more examples. Okay. So let's do our next example here. Let's do something that is a little bit more involved because it involves complex number arithmetic. Here is where you're going to see where some of the confusion comes in with key identities, because you have to understand a little bit about complex algebra. So the example is y double prime plus 2y prime plus 10y is equal to cosine of 2t. Okay. All right. So how does How does this work? Well, same as always. First thing, characteristic polynomial is z squared plus 2z plus 10. We could do this in our sleep by now. Right, so this is z plus 1 squared plus 3 squared. So roots, again, are minus 1 plus or minus 3i. Okay, so homogeneous solution, c1 e to the minus t cosine of 3t plus c2 e to the minus t sine of 3t. All right, there it is. Okay, now this time our right hand side is a trig function. It's cosine 2t. It's definitely in characteristic form. What's the degree of this thing? Still 0. What's characteristic now? Oh, characteristic has non-zero imaginary part. It's 0 plus I times 2, right? So it's 2i. Its multiplicity, well, 2i is not a root of the characteristic polynomial, so its multiplicity is still 0. There we go. So, right, just to beat you over the head with it, key identities process. I now want to evaluate the key identities at this characteristic that I found, which is just 2i. And evaluating key identities, I'm going from the 0th key identity, that's the m, to the m plus dth key identity, which is 0 plus 0 key identity. And I'm using algebra after that. So I really, according to this, should only need the original, the 0th order key identity itself. So just to write out my key identity, L of e to the zt is equal to p of z e to the zt. And I'm evaluating that at z, which is the characteristic here, which is 2i. So this tells me that L of e to the 2it is equal to p of 2i e to the 2it. Now you see some things are going on. Some things are a-brewin'. Okay, some things are a-brewin'. So what do I mean by this? Well, I look at this and I say, how is this going to be the same as cosine 2t? Well, it's not, just looking at it. First of all, I'm going to get rid of this p of 2i. I'm going to divide both sides by that. So this is L of 1 over p of 2i times e to the 2it. And that's equal to e to the 2it. But I want this right-hand side to be cosine of 2t. It doesn't look like that, right? But it's close. Notice, what is the real part of e to the 2it? Well, e to the 2it is really cosine of 2t plus I sine of 2t. What's the real part of cosine of 2t plus I sine of 2t? Cosine of 2t. That is exactly what we want on the right-hand side. So really what I need to do is take the real part of both sides. Can I do that? Can I take the real part of this and the real part of that and be happy? Yes. So I take the real part of L of 1 over p of 2i e to the 2it is equal to the real part of e to the 2it, which is cosine of 2t. Now, let's pause for a second. What if this was sine of 2t? What would I have done here instead? If I wanted this right-hand side to be sine of 2t instead of cosine of 2t, instead of taking the real part here, I would have taken the imaginary part. So this process would be exactly the same, but at this step, I would take m of this rather than the real part. Okay, I'd take the imaginary part. Okay, so this is what I get. Well, it turns out that the real part of L, this can be factored through L, and that's the only time I'm going to mention that. From now on, I'm just going to go through. So what this means is that L of the real part of 1 over p of 2i times e to the 2it is equal to cosine of 2t. And so we have found our particular solution. Y, so p of t, is this thing. It's the real part of 1 over p of 2i e to the 2it. You might say, oh, I'm happy. That was actually easy. Well, I need to actually figure out what this thing is. Okay, so I need to figure out what this thing is. And this is where that complex algebra comes in. So the first step, what's p of 2i? Recall that p was z squared plus 2z plus 10. So p of 2i is 2i squared plus 2 times 2i plus 10. Right? So what is this? This is 2i squared is 4i squared plus 4i plus 10. But I squared is minus 1, so this is minus 4 plus 4i plus 10. So this is 4i plus 6, or 6 plus 4i. So then what is 1 over p of 2i? This is 1 over 6 plus 4i. But how do I divide by a complex number? This is the conjugate, 6 minus 4i, divided by the modulus of this thing squared. So this is the modulus of 6 plus 4i squared. So this is 6 minus 4i over the modulus of this thing squared is 6 squared plus 4 squared. Right? Okay. So then what is this? 36 plus 16. So this is 6 minus 4i divided by 36 plus 16 is what? 52. So this is equal to 6 over 52 minus 4 over 52i. If I reduce this slightly to maybe make my headache not as bad, this is 2 times 3. This is like 2 times 26. So this is 3 over 26. Right, minus, this is 2 times 2. This is 2 times 26. This is 2 over 26, or 1 over 13. Okay. So that's what I get. So 1 over p of 2i is this. So then, what is the real part of 1 over p of 2i times e to the 2it? This is the real part of this thing, 326 minus 113i, times e to the 2it, which is cosine of 2t plus I sine of 2t. In order to figure out what the real part of this is, I have to expand this and make sure that I'm looking only at the terms that don't have an I in them. So this is the real part of, let's expand this entirely, FOIL this if you like. So this is the real part of 326 cosine of 2t, right, plus 3 over 26i sine of 2t minus 1 over 13i, sorry, cosine of 2t, minus 1 over 13i squared sine of 2t. Simplify. I squared is minus 1. So this is the real part of 3 over 26 cosine of 2t plus 1 over 13 sine of 2t plus I times stuff, right? 3 over 26 sine of 2t minus 1 over 13 cosine of 2t. But the real part only picks out the stuff that doesn't have an I on it. So all this stuff it ignores. And so the real part of that is 3 over 26 cosine of 2t plus 1 over 13 sine of 2t. That's it. And that's what my particular solution is. Okay. You can go back and check with the undetermined coefficients that we did, and you will see, indeed, this is exactly the same particular solution that we found. Of course, the general solution from that point would be, well, let's just go ahead and do it for completion's sake. So general solution to the original question is y of t, which is the homogeneous part, which I'm not going to write out again, plus the particular solution, right? That's how that goes. Okay. So this is a great example that shows you all the sorts of arithmetic that you might have to do for these kinds of problems. Let's keep going. More examples. So that's the only way to acquire skill here, is to just keep doing these over and over and over again. So let's do more examples. Let me see here. What's the next? Yeah, here's a good one. So y double prime plus 9y is equal to 4 cosine of 3t. Okay. So, what do we do here? Well, the characteristic polynomial is z squared plus 9. This has roots plus or minus 3i. So the homogeneous solution is c1 cosine of 3t plus c2 sine of 3t. All right, because the real part of this is 0. Okay. So f of t, of course, is 4 cosine of 3t. Well, alright, so f of t is 4 cosine of 3t. So degree is still 0. Its characteristic is 0 plus I times 3, or just 3i. Its multiplicity is 1. Because 3i is indeed a root of the characteristic polynomial. It's a simple root of the characteristic polynomial, so it's a root of multiplicity 1. So there we go. So degree 0, characteristic 3i, multiplicity 1. Okay. How does this affect what I do here? Well, again, key identities process. I'm evaluating the key identities at the characteristic, which in this case is 3i. And I need m through m plus d, so the first through the first. So I should only need the degree 1 key identity, which is this one. Let's write that out as always. We write out the key identities that we are going to use, and then we do our evaluation. So L of t e to the zt is equal to P of z t e to the zt plus P prime of z e to the zt. Okay, and I want to evaluate this at Z is mu plus I nu, which is 3I. So if I do that, what I get here is L of t e to the 3it is equal to P of 3I t e to the 3it plus P prime of 3I e to the, 3it. Well, let's just hold our horses for a second. P of 3I, what is that? P of 3I is 3I squared plus 9, but 3I squared is 9I squared. So that's 9 times minus 1 plus 9. So minus 9 plus 9, that's 0. This is 0. What's P prime of 3I? Well, let's see. What is P prime here? So P prime of Z is actually just 2Z. So P prime of 3I is 6I. Okay, cool. So P prime of 3I is 6I. And so what we get here ultimately is L of t e to the 3it is equal to 6I e to the 3it. Now, what I want here is I want 4 cosine of 3t here. So if again I divide through by 6i just to make my life easier, I get L of 1 over 6i t e to the 3it is e to the 3it. But I look ahead and I say, well, what I'm really going to want here is 4. So I want this to be a 4 here so that when I take the real part, I'm going to get 4 of cosine 3t. So really, this is what I'm looking for. So I need this to be a 4. Okay. And then I need to take the real part. So L of the real part of 4 over 6i t e to the 3it is the real part of 4e to the 3it. But the real part of 4e to the 3it is 4 cosine of 3t, which is exactly what I wanted. So this is my particular solution. Now a couple things here. One, if this on the right-hand side had been 4 sine of 3t, then at this step, what would I have done? I would have done everything exactly the same up through here. The only thing is that at this step, instead of taking the real part, I would have taken the imaginary part. That's it. Okay, otherwise it would have worked out the same way. Okay. All right. And so, this is going to be my particular solution. So y sub p of t is the real part of 4 over 6i t e to the 3it. All right. But I actually have to figure out what this thing is. Okay. So let's do that. So I want to first say what is what's 1 over 6i? Well, if I just follow my pattern, right, this is the conjugate over the modulus. What's the modulus of this thing? So this is, or modulus squared, sorry. So this is 0 squared plus 6 squared, right? So that's, so modulus squared would be 36, right? So that's what we're looking at. So we are looking at minus, so we're looking at minus I over 6. If you don't believe this, right, if you are confused about your computation, you can always check. How can you check? Well, if 1 over 6i is going to be what I claim it is, then whatever I find here, when I multiply it by 6i, I should get 1. So what is 6i times minus I over 6? The 6's cancel, and I get minus I squared. Oh, that's 1. Yeah, okay. So that's how this should work, right? All right, so minus I over 6 is exactly what we get here. So then 4 over 6i t e to the 3it, what is that? Well, that is minus 4 over, sorry, minus 4i over 6 times t times e to the 3it is cosine 3t plus I sine 3t. So if I expand this a little bit, this is minus 4i over 6t cosine of 3t minus 4i squared over 6t sine of 3t. The I squared is minus 1, so this is 4, so this is minus 4i over 6t cosine of 3t plus 4/6 t sine of 3t. Okay, but then what's the real part of this? So what's the real part of this? Well, it's the part that doesn't have an I in it, so that is ignored. The real part of this is 4/6, which is 2/3 t sine of 3t. Hey, this is my particular solution. That's it. And the general solution is y of t is homogeneous solution plus particular solution. There it is. Okay. Again, go back and check. We did this exact same example with undetermined coefficients. You can go back and check that when we did it with undetermined coefficients, we ended up with the same thing here. Okay. All right. So we have done a ton of examples. Let's do maybe one more so that we actually have. Let's do something else. Let's do one that has maybe let's do one that has a degree that is maybe bigger than 1. So let's see here. Yeah, so I think we did one of these things before, so that you can see how this works. Let's see, how do I want to? Yeah, let's do this one. So let's do y double prime plus 2y prime plus 10y is equal to 4t e to the 2t. Okay. This is an old friend by now. Characteristic polynomial z squared plus 2z plus 10. So our roots are minus 1 plus or minus 3i. So homogeneous part is c1 e to the minus t cosine 3t plus c2 e to the minus t sine 3t. Okay. F of t in this case is 4t e to the 2t. So we finally are now doing one where the degree is 1. The characteristic mu plus I nu is what? E to the 2t here, so this is 2 plus I times 0, so it's just 2. It's a real characteristic. What's the multiplicity? Well, 2 is not a root of this characteristic polynomial, so the multiplicity is 0. Alright, let's review what the key identities process says. Remember, evaluate key identities at the characteristic. Characteristic is 2 in this case. And the key identities I use are the m through the m plus d-th. Here we got something different. So this is the 0th through the 0 plus 1, the first. So, according to this process, I need the 0th key identity and this first order key identity. let's see how this works. L of e to the zt is p of z e to the zt. That's the 0th order. The second is L of t e to the zt is equal to p of z t e to the zt plus p prime of z e to the zt. Now I want to evaluate both of these at z is equal to the characteristic, which is 2 in this case. So I get two expressions here. I get L of e to the 2t is equal to p of 2 e to the 2t. And I get L of t e to the 2t is equal to p of 2 t e to the 2t plus p prime of 2 e to the 2t. Okay. So let's plug in some things. So first of all, p of 2, as we saw, this is 2 squared plus 2 squared plus 10. So 4 plus 4 plus 10, so that's 18. Okay, so p of 2 is 18. What is p prime? P prime of z is 2z plus 2. All right, so p prime of 2 is 2 times 2 plus 2, so that's 6. So rewriting these, this is 18e to the 2t. And here, this is 18t e to the 2t plus 6e to the 2t. Okay. So, what do I do here? When the key identities process told me to use algebra to find particular solution, there's a lot going on in these quotes, use algebra. All right, we've already seen some examples of how this works. Now we get to see another example. So what do I want on the right-hand side here? I want 4t e to the 2t, right? The idea is to isolate something that looks like 4t e to the 2t on this side. So here's t e to the 2t. I don't want 18 here. I want that to be a 4. And I don't want this 6 e to the 2t to exist, right? I want it to go away. Well, if I want it to go away, what I can do is I can divide, I can multiply this by 1/3, which turns it to 6 e to the 2t, and then subtract it from this equation. And I want to keep track of that here. How do I do that? So if I'm going to subtract 1/3 times this first line, right, from this second line, this would be, so since L is linear, this would be L of t e to the 2t minus 1/3 e to the 2t. And what that would be is 18 t e to the 2t plus 6 e to the 2t. 1/3 e to the 2t, hitting it with L, gives me 18 e to the 2t. So minus 1/3, 1/3 e to the 2t would give me 6 e to the 2t here, right, when I hit it with L. So minus 1/3 e to the 2t here would give me minus 6 e to the 2t. Those cancel, and I'm left with 18t e to the 2t. Now, I'm not done yet, because actually I'm not satisfied here. I want this 18 to be a 4. Right? That's what makes it equal to my original right-hand side. So if I want this 18 to be a 4, what do I have to do? I have to multiply by 2/9. I need to multiply by 2/9. So multiply both sides by 2/9 here. So then L of 2/9 t e to the 2t minus 2 over 27 e to the 2t is equal to 4t e to the 2t. So I finally matched this up with the right-hand side here. And so this thing that I've kept track of here, doing my algebra, is my particular solution. So y sub p of t is 2/9 t e to the 2t minus 2 over 27 e to the 2t. And I want you to notice that this is exactly the same as the undetermined coefficients method gave us when we did this exact same example. Right? This was exactly the same thing. And this is with a lot less effort. Undetermined coefficients, we had to do a lot more algebra than this. Okay. So this may be a little bit confusing and a little bit tricky when you first do this, but that's why you just have to do example after example after example. Okay. And that's that. So that's key identities. Right? You are free to use either of those so long as you have a linear, so this linear constant coefficient equation with the right hand side in characteristic form. Here's a question though. How do I solve the following? Let's do y double prime plus 2y prime plus 10y, our favorite left-hand side. And let's say that is equal to t e to the 2t cosine of 3t plus e to the 2t sine of 3t plus cosine of t. So, how do I solve this? The left-hand side, linear, constant coefficient. So it's the only other thing I need to be able to apply either undetermined coefficients or key identities. Well, I need this to be in characteristic form. Is it? No, it's not. This, if I ignore this term, this is in characteristic form. This has degree, that is 1. It has characteristic, I'll call it mu sub 1 plus I nu sub 1. And its characteristic is 2 plus 3i. And it has multiplicity. Its characteristic is 2 plus 3i. This has roots minus 1 plus or minus 3i. So neither this is not a root of this thing. So its multiplicity is 0. Okay. But this, while this is a thing on its own in characteristic form, these two things together combined into a single function are not in characteristic form. This is in characteristic form on its own, though. It has degree 0. It has characteristic, I'll call it mu sub 2 plus I nu sub 2, which is 0 plus I. And since I is not a root of this, it has multiplicity 0. So really what we have on the right-hand side, this is not, right, f of t, which is the whole thing here, if this whole thing is f of t, is not in characteristic form. Okay, it's not in characteristic form. So you might say, well, we just can't use undetermined coefficients or key identities to solve it. But it turns out that while it's not in characteristic form, it's made up of two things that are in characteristic form. So it's really f of 1 of t plus f of 2 of t. And each of these are in characteristic form with degree, characteristic, and multiplicity indicated here. This is an example of what's called compound characteristic form. Okay, I believe that's what he calls it in the textbook. Let me just check to make sure that that is the name he uses. Composite characteristic form. I knew that it was something similar to that. So composite will stay consistent with the textbook. So this is called composite characteristic form. Okay. So what is the... So the answer is I do key identities / undetermined coefficients for each piece, for each component. So, if something is in composite characteristic form, you have to do key identities or undetermined coefficients for each piece. So if it's in two pieces that are in characteristic form, you would have to do key identities for or undetermined coefficients for this piece fully, and then do it for this piece. For each component, you would get a particular solution. You would get y sub p sub 1 of t and y sub p sub 2 of t. And then what would your y sub p of t function be? Oh, the sum of those. Now, I did it here for two pieces. If you had, this thing split into 10 pieces, right, where each of the 10 pieces was in its own characteristic form, you would have to do this process 10 times and then sum the results to get your particular solution. Okay? So this can be a headache, but yes, you can in fact do it. So, just because the thing is not in characteristic form as written doesn't mean you still, can't use undetermined coefficients or key identities in some way. You can, all right, if it's in composite characteristic form. So if it's in composite characteristic form, you can do this. You just have to do it multiple times, okay? Now, if it's not even in composite characteristic form, then you're out of luck when it comes to using these methods. So we'll see what you have to do for more general things. And that's where I'll start tomorrow. So tomorrow I will start the lecture basically with, I'll start the lecture with an example of variable coefficients and how we are going to go about solving those things. So variable coefficients next on the menu before I get to sort of the rest of this stuff. By midway through next week, we will have finished. We'll have finished chapter 2. Maybe not, including Laplace transforms. We might not have finished chapter 2 by that time, but we will be getting close. Once we finish Laplace transforms, we will be very, very close to the end. So. We should have about 2 weeks for chapter 3 material, which will be plenty of time for us to go through all of that stuff. So anyway, that is the deal. So I am going to post a really quick homework for you all soon that will be due in a couple days. Your exam will be posted this Friday, and it'll be due on Monday, I guess, is what I'll do. And so that will be that. So anyway, let me, like I said, let me know if you have any questions, and I will see you